So I'm almost done with the test you turned in last week. I want to spend time tomorrow kind of going over that. And one thing that I decided is that I'm going to kind of quit while I'm ahead. And we're going to start reviewing like right now, okay? So we finished 12.3 last time, and I'm going to consider that to be kind of like a good place to stop. Now, I could have talked about arc length and curvature. That's something that will be discussed anew in Calc 3 anyways. So we'll kind of stop with the acceleration and velocity discussion that we were having and seeing that play out in the projectile motion stuff that we were discussing last time. But I want to back up today and go to the beginning of chapter 8, okay? In the last test, you had to go back even into the end of chapter 9. You had to study chapter 10 and 11, so I'm hoping that's sort of fresh. But I'm going to back up to chapter 8. Remember, this first section was just on what I called tricky integrals, okay? There were a bunch of rules that you had to have, and they were stated right here at the beginning of the section. By the way, this is the ebook that you all have access to in WebAssign, okay? You can easily kind of click around in here and see various things. Sometimes it's kind of fussy and dependent upon which browser you happen to be in. It'll give you some issues with security and whatnot, but if you click on that little lock symbol up there, a lot of times that you'll be able to allow something that was maybe being disallowed. I'm looking at this in Chrome, which seems to work okay. So the basic integration rules that you probably should have had in your cognition at the end of Calc 1 are listed over here on the left. Probably the trickiest of which are these so-called, trig integrals or arc trig integrals down here, involving the arc sine, arc tangent, and arc secant. But the main ones I want you to focus on are number 18 and 19, right? Those arc sine and arc tangent ones. Those are the basic forms there. The other ones are mostly straightforward, except for this obnoxious one right here, right? The integral of secant, which is logarithm, the absolute value of secant plus tangent. But you probably have that somewhat burned into your cognition as it is. To see the sorts of things we had to do, I think this first example is kind of instructive. The very first example in the section says a comparison of three similar integrals, where all that's happening with these three integrals, A, B, and C, is you're simply going from 4 to 4x to 4x squared in the numerator, and the denominator is staying the same. This first one, if you have 4 over x squared plus 9, you can easily put it into a form that arctangent applies to. Now they like very carefully at each equality kind of write what it is they're doing. So basically you factor out 4, you put this thing in the form 1 over x squared plus 3 squared, and then you see that it has this form of number 19 right here. You see it? Where u is basically x and a is basically 3. And then you just straight apply the arctangent rule right here. 1/3 arctangent x over 3 plus a constant. And there is your answer right there, okay? So that one worked out kind of nicely. Now, what's going to be different if I slap on an additional factor of x in the numerator? Well, without looking at letter B, what do you guys think? What would you do in that case if you had a 4x instead of just a 4? What are you going to do instead? Substitution. Yeah. So that's precisely what they do here. They say 4x over x squared plus 9. They factor out a 2 so that the numerator is exactly the derivative of the denominator. And then they proceed to do a u substitution. They put u equal to x squared plus 9, and all is right. What happened to the absolute value? So you get du over u, by the way, you get logarithm absolute value of u, logarithm x squared plus 9, because that's what u was. U was x squared plus 9. What happened to the absolute value? That's always positive, so who cares about absolute value, right? X squared plus 9 is always positive. Okay? Lastly, what's going to happen if you have 4x squared over x squared plus 9? Well, that, my friends, is going to involve some long division, if you want to do it that way. Or, I mean, there's some other trickery that you could do, like you can add and subtract 36. I mean, think about it for a second. If I add 36 and subtract 36, that's like adding 0 to the numerator. I'm talking about in the numerator here. If I add 36, that would be like 4x squared plus 36. That's exactly 4 times the bottom, isn't it? So that you could actually cancel top and bottom and just have 4, which is where that comes from. But then the minus 36 would remain, which gives us this, yes? But you could have also gotten to this point by simply doing polynomial division, right? And then we're back where we were in the first problem, aren't we? We have minus 36 over x squared plus 9. I know how to integrate 4. I mean, seriously, right? But this guy, I apply the arctangent rule to, just like I did before. And everything kind of works out nicely for us, okay? That's kind of a helpful thing to think through for the purposes of trying to get our mind back into what was going on in section 1 of chapter 8, okay? I want to go into, oh, by the way, what would you do here? So what would you be inclined to do on, well, they're already kind of giving it away right here. You can kind of see. Look at this one right here. The integral of x plus 3 over the square root of 4 minus x squared. They broke it up into 2 integrals, yes. And they basically said, well, look, this one I can do with a u substitution, correct? I can basically put u equal to what's under the square root. The x is almost the derivative of that. The second thing, 3 over 4 minus x squared, that you're going to apply the arcsine rule to, okay? And everything would collapse. You guys remember integration by parts? Hopefully, okay? Helps you deal with products of things. Okay, things like x logarithm of x squared e to the x sine of x. All of that can be dealt with using integration by parts. Remember, the general formula was this right here. Integral of u dv is equal to uv minus the integral of v du. And we even had a little acronym that helped us decide what to put u equal to. Remember what it was? I-late, I-L-A-T-E. As you read that left to right, that's what got priorities being put equal to u, right? I stood for inverse trig, L for logarithm, A for algebraic, T for trigonometric, E for exponential. Exponential had the lowest priority as being put equal to u. Why? Well, because exponentials are generally easy to find the antiderivative of, okay? And why is I inverse trig? Why is that something you want to put equal to u? Well, if I put it equal to dv, excuse me, I'm going to have to find the antiderivative of that, which is not desirable. You know what I mean? I'd rather take the derivative of an inverse trig function rather than integrate it, okay? Let's see, there's some nice examples here. Here's one with x e to the x. So the integral of x e to the x, what would get priority as being put equal to u? X, because that's algebraic, yeah? That's what they're basically doing here. They put u equal to e to the x, or sorry, no, that's the other option, and that's not a good option. They basically go through all of the different ways that you could do this, and they determine that the best approach is to put u equal to x and dv equal to e to the x dx. Okay, if dv is e to the x, then v is just e to the x, and du is dx. So you plug into the formula for integration by parts. It's going to be uv, which is x e to the x, minus the integral of v du. Well, v is e to the x, du is dx. Okay, and then we're good to go. X e to the x minus e to the x plus a constant. Yeah? And again, lest you doubt what's happening here with these antiderivatives, you could always check your work by doing what? How can I check that that's actually an antiderivative for x e to the x? Take the derivative, for crying out loud, and see if it gives you that. Yeah, and you could always do that. There are plenty of other examples here, but I just, oh, let's look at the arcsine one. That one's cute, right? Okay. So what about this? The antiderivative of arcsine, here it's actually a definite integral from 0 to 1. They want the antiderivative of arcsine from 0 to 1. That's cute, right? So what do you do? What do you do in this case? Well, clearly, you don't want to put dv equal to arcsine dx. You know what I'm saying? Then you would have to find the antiderivative of arcsine, which is exactly the problem that we are now doing. Yes? Okay? So a better approach is clearly to put u equal to the arcsine function, which, by the way, is what that acronym told us to do in the first place. Remember? Okay? So you put u equal to arcsine, and dv equal to dx, which means v is x, and du is the derivative of arcsine, which is 1 over the square root of 1 minus x squared dx. Plugging things in, you get arcsine of x dx, integral of arcsine of x dx is equal to x arcsine of x minus the integral of v du, which is given by this. And then all they do is basically a u substitution to do this antiderivative, yes? Now it's just a matter of doing a u substitution. But we wanted the integral from 0 to 1, so we plug in 1 and 0. Okay, if I plug in 1, well, if I plug 1 in, this square root is 0, correct? And it's going to be the arcsine of 1. What's the arcsine of 1? Arcsine of 1 means the angle whose sine is 1. What is that? What angle is such that the sine of it is 1? Pi over 2, which is where this pi over 2 comes from. And then you subtract this thing with 0 plugged in. Well, 0 is going to kill off this x arcsine of x, yes? And then if you plug 0 in here, you get 1. So you get pi over 2 minus 1 for the definite integral, okay? That's a couple of nice examples using integration by parts, okay? Trig integrals, that was the third section. So first section, tricky integrals, where we had to do stuff like, divide numerator and denominator, add and subtract the same thing, multiply and divide by the same thing. Okay, sometimes we even had to complete the square. Remember doing that in the tricky integrals section? There's some examples in 8.1 about that. Integration by parts was the second section. Trig integrals. That's where we were interested in integrating products of powers of sine and cosine or secant and tangent. Yeah. You will recall that we had some guidelines that helped move us along in that regard. Now, if you happen to have, okay, before you even look at this below, what about this example right here? Sine to the 5th times cosine, what would you do? It actually says it right there. I'm going to cover it up so you don't see it, yes? What would you do if you had sine to the 5th times cosine? What would be your approach? Well, do we have to do anything necessarily that complicated here, Daniel? Yeah, this one is just straight u substitution for sine. And you see the derivative of sine sitting right there. Yeah, so it kind of works out nice. This is what they say here. Okay. Basically, this thing becomes the integral of u to the 5th du if you put u equal to the sine of x. And it's just a straightforward thing. Now, remember, we had to utilize the Pythagorean identity for sine and cosine. Sine squared plus cosine squared is 1. And also, at times, we had to use the half angle identity for sine and cosine. Remember that? If we happen to have some additional factors of sine and cosine lingering on their own, we sometimes had to invoke the half angle identity for sine squared and cosine squared. Half angle. Okay? This was kind of our guiding principles. If you had sine to an odd power, okay, then what you would do is basically peel off one factor of sine right here. And then what's left? Well, an even, see, the reason this is an odd power, it's like 2 times an integer plus 1, correct? That's what an odd number looks like. What they're saying is, then you basically can just take the one factor of sine off, then you have an even power, which means you could write sine squared to the k, right? To something. And then you can simply replace sine squared with 1 minus cosine squared. This is kind of what Daniel was alluding to. Then you simply put u equal to what? What would you put u equal to in this thing? Cosine. If you put u equal to cosine, the derivative of that is almost sine, correct? It's negative sine, but you can make that work. Okay, so you do a u substitution at that point. What if the power on cosine was odd? Well, same story. Peel off a factor of cosine, and we're off to the races again. You just convert the cosine squared to 1 minus sine squared once the power on cosine is even. And a u substitution will do the trick. Okay? What about when the powers of both sine and cosine are even? If there's an odd power anywhere, we do this thing where we just peel off the one and convert to the other one, yeah? And then do a u sub. If both the powers are even, then you just have to start utilizing sometimes they're called the power reduction formula, but I like to call them the half angle formula, okay? So that's slightly annoying when you have to do that, but whatever, right? So like, here's an example. Sine to the third times cosine to the fourth, okay? Just looking at that, sine to the third, cosine to the fourth, the power on sine is odd, yeah? So you're going to peel off a factor of sine, which is what they do here. They replace sine squared with 1 minus cosine squared. And that is perfectly suited for a u substitution. They distribute the cosine to the fourth on through and get cosine to the fourth minus cosine to the sixth times the sine function. And then you basically do a u substitution at that point. I'm not sure why they decided to make this so complicated and rewrite it as 2 integrals. They could have just done u equal to cosine at this point right here, okay? And then basically everything works out nicely, yeah? U substitution does the job. Okay, interesting. What about this one? This one's curious. Here I have like a square root of sine right here. Well, here I can do a similar thing. Cosine cubed upstairs. I can still peel off a factor of cosine, yeah? And say, well, cosine is basically the derivative of sine. So I can convert the cosine squared to 1 minus sine squared, and then we're off to the races again. I can basically just put u equal to sine of x at this point. And for everything that they're doing right here, that's basically what's happening. They're putting u equal to sine of x. And the derivative of sine of x is cosine of x. So that u substitution allows us to move forward, okay? Here's one that involves power reduction. Okay, so cosine to the fourth power, what do? Well, you write that as cosine squared squared, then you use power reduction, or use the half angle identity. And then when you square that out, you get another squared right here. So what do you do? What do you do with this cosine squared? You do it again. Use the half angle identity again. Cosine squared 2x is equal to 1 plus cosine of 4x over 2. And then you get it down to where the integrals are nothing but stuff that we know, like cosines and integral dx's. Okay, so that's that. There was one like little caveat, which, I mean, I don't really want to, Wallace's formula, I'm not going to be concerned about you knowing that. But there was one little caveat about products of cosines and sines that have different angles. We'll see that at the end of the section. But secants and tangents, I mean, it was a similar kind of trickery that was going on, okay? We had all kinds of rules for how to deal with those. I won't go into a ton of detail there, but it was fairly similar, if you will recall. But I did want to point out, let's see, where is this thing? Yeah, right here. Remember we had these weird, and again, I'm not going to make you memorize any of this stuff or anything. I just want you to be aware of it. They had these products of sines and cosines of different angles. They basically used the sum and difference formula to split up the integral into a couple of pieces. There was a couple of WebAssign problems that you had to do that were kind of like that, okay? Trig substitution, that was the one that typically gives students the most trouble. Basically, all we're doing is using the Pythagorean identities for sine, cosine, secant, and tangent to make an integral a little bit more complicated at first by introducing sines and cosines, secants, and tangents. But the point is to try to make the square roots vanish, yeah? Try to turn something that isn't a perfect square into a perfect square. Kind of like this right here, square root of a squared minus u squared equals a squared minus, what if you put u equal to a sine of theta? Well, a squared minus a squared sine of theta is this. And once you do that, you take the square root, but you have to be careful to ensure that the thing you're dealing with is positive, right? We've talked about that at length, yes? When you're doing an indefinite integral, a lot of times you just kind of assume that that's the case. But you have to make sure you're integrating on an interval in the definite integral case where stuff is all positive. Remember, we had these reference triangles that we were dealing with at times to go back and forth between things. Let's just look at this example. Integral of dx over x squared times the square root of 9 minus x squared. Well, look, what you would do is you would put x equal to 3 sine of theta. Okay, so that this thing would end up being 9 minus 9 sine squared, which is just 9 cosine squared. If you put x equal to 3 sine of theta, though, dx ends up being 3 cosine of theta. And the square root of 9 minus x squared is 3 cosine of theta as well. Kind of assume that everything is nice and positive. And of course, x squared, which is right here in the denominator, is just 9 sine squared. And this is why we did all the stuff with trig integrals from the last section, remember? Because a lot of times when you do trig substitutions, you end up with a trig integral. So you end up with powers of sines and cosines, and et cetera, that you then have to deal with, okay? So you plug stuff in, dx is this, x squared is that, square root of 9 minus x squared is 3 cosine theta, okay? And then when you cancel stuff, you end up with 1/9 d theta over sine squared of theta. But 1 over sine squared is just cosecant squared, okay? And you may recall from section 1 that the antiderivative of cosecant squared is almost cotangent, right? The integral of secant squared is tangent, yes? The integral of cosecant squared is almost cotangent. There's just a minus sign difference there. Okay, and then how in the world did they figure out what cotangent of theta was? Well, they use this little reference triangle right here. They say, well, look, for crying out loud, sine theta is x over 3. So they make a little right triangle with theta right here. And they say sine theta is opposite over hypotenuse, yes? So sine of theta is x over 3. So we put those things in there. In this third side, we solve for cotangent of theta. Remember, tangent of theta is opposite over adjacent. Therefore, cotangent of theta would be the flip of that, yeah? Adjacent over opposite, yeah? So you would do square root of 9 minus x squared over x. And that's where we get, that's where that comes from right there. Okay? The examples in the section are laid out pretty nicely here. I think they do a pretty good job. Any questions on that? Questions? Let's see. Right, so these examples are fairly similar for the most part. Let me go to partial fraction decomposition. Okay. Now this is the one, if you will recall, where we had, you know, to factor the denominator and then split the thing up and do a little bit of algebra. Remember that? Okay. So like in this example right here, that thing's pretty gnarly, okay? The way that they had to do that. I think that there's a better way to do this though. First, you can, how in the world did they come up with this? Look, up here, they had to do some crazy stuff with like a trig substitution, and they ended up here. And you're like, well, that seems pretty simple. There must have been an easier way. And it turns out there was. You would factor the denominator. How does x squared minus 5x plus 6 actually factor? X squared minus 5x plus 6, how does that factor? X minus 2, x minus 3. So you would say a over x minus 2 plus b over x minus 3, for instance, yes? Then we do stuff like, you know, bring it to a common denominator and deal with it that way. There's a little bit of algebra that has to be done. But look, this equals this, and of course, you know the antiderivative of those two things. But let's see how they go about doing this. Hang on, I think they're going to revisit that example down here. Yes, here it is. So you go 1 over x squared minus 5x plus 6. That factors like this. So you write it this way, yeah? If you bring this to a common denominator, by multiplying a by x minus 2 and b by x minus 3, you end up with this. And here it's easy enough. You can just plug stuff in if you want. There's another technique we talked about called comparing coefficients, which you may or may not remember. But this way we figure out what a and b actually are. And that gives us the appropriate partial fraction decomposition. And then we are able to integrate, because the integral of 1 over x minus 3, that's easy. That's just logarithm absolute value of x minus 3. Similarly for the second thing there. Okay? Interesting. They have lots of examples in here to that end. Partial fraction decomposition, I know, can get fairly complicated, especially when you have so-called quadratic factors that cannot be reduced down. Like for instance, in this case right here. Look at this, x squared plus 4. Can you factor that? Nope. We factor this though to x times x minus 1, x squared plus 4. So the breakdown of this thing would be a over x plus b over x minus 1. And then what would be x squared plus 4? Well, you would have cx plus d right there. And then you can kind of do a little bit of algebra to sort out what those things are. Okay, and you end up with this. How do you integrate 2 over x? That's easy. Minus 2 over x minus 1, easy. 2x over x squared plus 4. You kind of break those up. That's easy to do with u substitution. And then this guy right here, you're going to use arctangent to handle that. Okay? Hopefully that kind of rings a bell a little bit. And then we had the section on repeated quadratic factors and repeated linear factors, where you kind of count up the powers, yes? And that's where the algebra starts to get real interesting, okay? But I want to talk about improper integrals. We didn't do this section on integration by tables. Indeterminate forms and L'Hopital's rule, I'm going to kind of skip over that. That's just, hopefully that's not too hard for you to remember, okay? An indeterminate form was something like infinity minus infinity, 1 to the infinity, 0 to the 0, 0 over 0, infinity over infinity. And the goal, to use L'Hopital's rule, was to always put the limit you're trying to compute in the form 0 over 0 or infinity over infinity. Okay? And then the improper integrals is where we first started using that. These are integrals where we had some significant problems going on. And we had to think about what was happening. Okay, so let's look at some examples here. What about the integral from 1 to infinity of dx over x? Well, we turn that into a limit as the upper limit goes to infinity. This is going to be logarithm of x. The antiderivative of 1 over x dx is logarithm of x. You plug in logarithm of b minus logarithm of 1, which is 0. And you know that that goes to infinity. So that integral diverges. That's what we say, okay, in that case. What about this guy right here? So let's do e to the minus x dx. Same sort of thing, integral from 0 to infinity. You replace the upper limit with a variable that goes to infinity. You do the antiderivative, and we're going to be doing the limit as b goes to infinity of negative e to the minus b minus e to the 0, which is just minus negative e to the 0, which is plus 1. Okay. And then you make the observation that e to the minus b, that as b goes to infinity, that goes to 0. So this thing converges to 1. What about this guy right here? I don't know if this thing isn't for some reason letting me scooch this over. I have to lessen this a little bit. The integral from 0 to infinity, 1 over x squared plus 1. The antiderivative of 1 over x squared plus 1. By the way, there's a typo here. What should this say? This is limit as b goes to infinity. What should this say up here? b, okay? You take the antiderivative of that, that's arctangent of x, and you plug in b and 0. The arctangent of 0 is 0. The arctangent of b as b goes to infinity, arctangent goes to pi over 2. Okay? So this thing goes to pi over 2. And there were times where we had to use L'Hopital's rule when we were doing these improper integrals. Okay? One thing that I would suggest that you do, and I think it's good, is you go into like the review exercises at the end of a section. Okay, so it's chapter 8, and you just go through and see if you know how to do these integrals. Yeah, that's great practice. Definitely go back and look through your WebAssign assignments as well to make sure you remember how to do these things. Now, some of them kind of cheat. They say use integration by parts, okay? To me, that's, maybe a little bit silly. I'd almost rather not be told what to do, that I would have to sort that out on my own, okay? But they have examples from each one of those sections in there. We didn't do the integration by tables section, so you can skip that. But I think there's a section in here where it doesn't tell you anything. Let me see. I thought there was, maybe not. But where does it say that? Using any method. Oh, these guys right here. So these guys are good ones. Yeah. So going through those, practicing some of those would be advisable for sure. Okay. Here's some improper integrals for you to practice. In fact, I think we did a few of these when we were reviewing for the test over chapter 8. There's actually a video on YouTube, by the way, that is a review of chapter 8. Yeah. That we did for the first test. So you could go look at that as well. Kind of help you out with your studying for sure. Okay. So this is what this is how I study. I just kind of look through the sections. I read through some examples. I go to the review exercises. I try to refamiliarize myself with what's going on in these sections. Say, oh yeah. I remember doing that for sure. Clicking through here and just kind of looking through things, that's to me sort of good study practice. Okay. Any questions on that? Questions? Yeah, Maria.
Is the exam going to be about the same difficulty as the last exam?
Yeah, I mean, I think that, yeah, I mean, sure, yeah. I mean, it'll just be similar to what you've come to expect, I guess. Okay. Other questions? I mean, there'll probably be some, multiple choice, maybe true and false on there, but then other problems as well. Yeah, Drake.
So it's like tables and stuff, or would just be like that series table that we have on.
Yeah, I think I might actually put a, right, so the series table, I might actually put, oh man, I don't know. I might actually put some like the quadric surfaces. Although, man, I sort of want you to know those, but yeah. But the quadric surfaces, man, I feel like the forms of those are pretty easy to remember for the most part. We had those 6 quadric surfaces that we learned together. But there is a chance I might put that on there as well. Okay, but I'm not gonna make a promise right now. Okay. Other questions? Well, that's all I have. Tomorrow, I want to spend significant time on going through our test and then talking about chapter 9 on infinite series, which to me is kind of the crux of the matter for sure.